And we're back and better than ever, still in 17-2, where we're exploring measuring and expressing enthalpy changes. At the end of the last podcast, we said that we were actually done with 17.2, and of course I was just kidding. We actually have quite a bit more to do. We wanted to discuss thermochemical equations and some of the stoichiometry that goes along with that. Alright, so let's take a look at this first reaction where you're combining calcium oxide and water to form calcium hydroxide. Anytime you put a metal oxide into water, it's going to be forming the hydroxide version of that. And in this case, this reaction is going to release 65.2 kilojoules of energy along with the reaction of 1 mole of calcium oxide and 1 mole of water. And so you can write it in as a product because the energy is being released as a product. Another way that you could express this is to simply write out the equation and then off to the right simply state the enthalpy change. Since this is an exothermic reaction, it's a negative change and it is 65.2 kilojoules of energy. Now that is per mole of reaction, meaning if you run this reaction exactly as it is written, per mole it's going to release that much energy. In the next set of equations, we're going to have an endothermic process. It's the decomposition of sodium bicarbonate, and it actually absorbs 129 kilojoules of energy. And so because it's absorbing that energy, we put it on the reactant side. Of course, you could put it off to the right, just like you did before, where you express the change in enthalpy. In this case, it is a positive value because it's an endothermic process. It's absorbing the heat. It's absorbing 129 kilojoules of energy per mole of reaction, which includes 2 moles of this. So the decomposition of 2 moles of this will produce this much energy. It's per mole of reaction. Now the other thing that you have to consider is the physical states, because they do in fact matter. When you decompose water in the liquid phase, it's an endothermic process. You have to put energy in, and delta H is going to be a positive 285.8 kilojoules. However, if you did it in the gaseous phase, the delta H is actually only going to be a positive 241.8 kilojoules for a difference of 44 kilojoules. So it does matter what the physical states are, and in fact we might come back and revisit the reason why this is 44 kilojoules or what that actually represents in 17.4. But for right now, you should realize that the physical states of the reactants and products do matter. Alright, so let's go ahead and jump into a practice problem here. Using the thermochemical data above, calculate the amount of heat in kilojoules required to decompose 2.24 moles of sodium bicarbonate. Alright, so if you're starting with 2.24 moles of sodium bicarbonate, this is simply a stoichiometry problem, because if you know how much of this you have, you can calculate how much of any of these you would produce. Or conversely, if you know how much of this that you have, you can calculate how much of this that you need. And so the ratio is simply going to be a 2 to 129. 2 moles of this will produce 120, or will require 129 kilojoules. So automatically, since you're starting with 2.24 moles, you have more than the 2 moles. You should expect to require more than the 129 kilojoules. So the ratio will be 129 kilojoules of heat is needed for every 2 moles of sodium bicarbonate. It works just like a mole ratio, except in this case it's just a regular ratio of energy to moles of sodium bicarbonate. The moles of sodium bicarbonate divide out, and then you have 2.24 times 129 divided by 2, and it looks like we have 144 kilojoules of energy. That's how much energy would be required to decompose the 2.24 moles of sodium bicarbonate. Alright, moving on to the next one. Using the thermochemical data above, calculate the amount of heat in kilojoules released when 20.0 grams of calcium hydroxide forms from the calcium oxide in water. So going back up to that reaction, this much heat accompanies 1 mole of calcium hydroxide. So just like in any other stoichiometry, you change everything into moles, then use your ratio. We're going to do that once again. So coming on down, we have 20.0 grams of calcium hydroxide. To change it into moles, we use the molar mass. 1 mole of calcium hydroxide has a mass of 74.10 grams. Of course, the grams divide out top and bottom, and now we can use our ratio. It was 65 point something. Was it 65.9? Nope, 65.2 grams or kilojoules. Excuse me. So 65.2 kilojoules of heat is released with 1 mole of calcium hydroxide. And notice all the units divide out. You're left with kilojoules. You're looking for kilojoules, and so we're going to take 20 times 1 divided by 74.1 times 65.2, and it looks like we have 17.6 kilojoules of energy is released. Now notice we don't have to put the negative sign in there because it already says release, so we're already saying that it's leaving the system, where delta H would in fact be negative. Now we could also, instead of having tables where you give individual data for every single reaction, you can have something like heats of combustion, which actually give you the heats that are released when these substances are burned with oxygen. That's what combustion means. So all of these energies are released when these molecules are reacting with oxygen, and notice it is per mole. It is per mole. So let's go ahead and take a look at a few of these problems. First of all, with the burning of methane. When you burn methane with oxygen, it produces carbon dioxide and water, as does the combustion of any hydrocarbon. According to the table, it's going to release 890 kilojoules of energy. Now notice that we simply add that in as a product, or you can say that the delta H of combustion is going to equal a negative 890 kilojoules. That'd be another way to express the energy change there, or the enthalpy. Alright, so here's the question. Which fuel source is going to release more energy per gram? Hydrogen, or this would actually be octane. This is one of the molecules that's going to be in gasoline. In fact, that's the rating that you have at the gas pump, is going to be the octane rating. So let's go ahead and try that. If you have 1 gram of hydrogen, or if you have 1 gram of octane, which one releases more energy? So we're going to take 1 mole of hydrogen is going to weigh 2.016 because it's H2 grams. The grams divide out, and if you double check the energy, hydrogen releases 286 kilojoules per mole of hydrogen. So it's going to be 286 kilojoules per 1 mole of H2 reacted. And so if we perform that calculation, 1 divided by 2.016 times 286, we get 142 kilojoules of energy per 1 gram of hydrogen. If we do the same thing with the octane, octane has a molar mass of 114.22 grams per mole. So we divide by the 114.22, and now the energy that's going to be released for octane is down here. It's 5,471. So it releases 5,471 kilojoules per 1 mole of octane. So therefore you take your 1 divided by 114.22 times 5471, and we actually get 47.9 kilojoules of energy per gram of octane. So while looking at the table, you might say, man, octane has a tremendous amount of energy that gets released. And it does. Hydrogen appears to have a very small amount of energy released. Well, per mole, that is true. However, when you do it by mass, which is oftentimes the deciding factor, hydrogen releases a tremendous amount of more energy than the octane does per gram. This releases a lot more energy, and in fact that's one of the reasons why we're exploring hydrogen as being used as our replacement fuel for fossil fuels, because in fact it does release a lot of energy per gram of hydrogen. Okay? Now this really does conclude 17.2.